Well, hello, and welcome to another episode of Quantitative Bytes. So today I would really like to continue with a series that we've been doing where I'm looking at developing a simple 2D primitives library that works with SDL in C++, so that I can use it to draw simple two-dimensional shapes. So as we've covered in the previous videos, SDL provides basic functionality for drawing into a window with C++ code. It's nice to use because it's extremely multi-platform, and it allows us to draw points and lines and rectangles, but if we want to draw more complicated things, then we don't really have any options for that. So I've set out to create a simple library that will allow me to draw circles, filled polygons, lines of specified thickness, and potentially a variety of other shapes as well. In the last episode, we were looking at circles, and in fact the previous episode and the previous but one episode really focused on circles. So particularly in the last episode, we focused on how we can speed up or accelerate the process by which we draw circles. And we were able to achieve that by realizing that we can exploit the inherent vertical and horizontal symmetry in a circle, meaning that we then only really need to check a quarter of the pixels within our bounding box rather than having to check absolutely everything. And we looked at how we could implement that in code and we could make it faster. Now, when I finished the episode last week, I left it up as an exercise for the viewer to see whether they would also be able to exploit the diagonal symmetry that a circle has. So it is, in principle, possible actually to reduce the number of pixels you need to check down to as low as 12.5% by utilizing diagonal symmetry. I haven't myself gone on to look at that. What I've been focusing on over the last week instead has been implementing the code to do filled polygons. Now, I must confess I haven't got as much done in the last week as I had hoped to. I haven't been feeling that well. Thankfully nothing that serious. But even so, I haven't achieved as much as I would have liked. However, before we really dive into this week's episode, I just want to quickly recap on what we were doing. So if you see the diagram here to my right, then this is the class structure diagram that we're working to. So what we've done is we've created, or what I've done is I've created a base class called object, and then from that, all of our different classes representing our different shapes inherit from that. So we have a class for circle, and what we're going to talk about today will be the class for filled polygon, and then we have the classes for other special case shapes that we might want to do. So that's the basis, well, the basic structure of what we're working to. The actual process by which we're going about generating these shapes doesn't vary that much depending on what the shape is. So the flowchart that you can see here shows the basic outline of everything that we're going to do. So to begin with, when the user creates an instance of the class for a shape, we will create or compute the limits of a bounding box. So that tells the box that contains all of the pixels that then contain our two-dimensional shape. And then it's really very simple. So once we've got the bounding box, all we actually do is then loop through every pixel in that bounding box. And for every pixel, we check whether that pixel is inside the shape or not. If the pixel is inside the shape, then obviously we render a pixel at that point, and if the pixel is outside of the shape, then obviously we don't do anything. Between our different shapes, really all that's going to vary is the process by which we calculate whether the pixel that we're currently looking at is inside the shape or not. Now, for the case of a circle, as shown here, this is actually very simple. The circle equation that you can see here essentially boils down to a signed distance function. And all we have to do is evaluate that equation given the center point of the circle and the current pixel coordinate that we're considering, and that gives us a value. If that value is less than or equal to 0, then we know that we're inside the circle. If it's greater than 0, then we know that we must be outside of the circle. And so we can very easily render a circle. And as I said in the previous episode, we focused on how to make that process faster, utilizing symmetry, but we don't need to worry about that. The basic process, is essentially the same. And in fact, we could represent a variety of shapes that way. Any shape that we could create a signed distance function for, we could, use this method to draw that. And that's something I hope to go on to look at in later episodes. However, in this episode, what I wanted to focus on is what I've been doing the last week, which really has been looking at filled polygons. Now, filled polygons are a slightly different case because we can't determine whether or not we're inside the polygon simply by solving some kind of signed distance function. The user could specify any arbitrary number of vertices in any arbitrary positions, and there's no way to make a signed distance function that would represent that shape. So we have to go about it a different way. Now, luckily, there is actually a fairly straightforward way of doing this, which I just want to talk about now very briefly, and then you'll see in much more detail when we go to look at the code in a moment, and I think it will then make a lot more sense. The basic theory is that if we consider a point, so consider a polygon such as the one shown here, and if we consider for the moment a point inside the polygon, now how can we determine algorithmically that this point is inside the polygon? Well, the easy way to do it is to cast a line out from the point horizontally out towards the edge, right to the edge of the bounding box. And then all we need to do is count how many times that line crosses the boundary of our polygon. And as you can see in this case, the point is inside the polygon and it crosses the edge exactly once, which is of course an odd number. So we get one edge crossing, which is 1. 1 is of course an odd number. If the point was outside the polygon, say it was over here to the far left of the polygon, then we cast the line in exactly the same way, but now we see it crosses the boundary of the polygon twice. Obviously an even number of times. And I'll leave it for you just to work this out if you like, and with pen and paper you can explore this and have a look at it. But it works out that for any point that is inside any polygon, regardless of the complexity, convex, concave, whatever, of the polygon, if the point is inside and you do this method of casting a line out horizontally, then that line will always cross an odd number of edges. And if the point is outside the polygon, it will always cross an even number of edges. So all we really need to do to determine whether a point is inside the polygon or not is to cast a line from that point out to the horizontally out to the edge of the bounding box, count how many times it crosses the edges of the polygon. If that number is odd, then we know we're in the polygon. If the number is even, then we know we must be outside the polygon. And that's actually it. It's pretty basic. And I'll leave it for you to check. The slight complexity comes when you actually think about how do I calculate whether I'm crossing the boundaries or not. We're going to come to that in a moment. What I want to do first is head over to the computer now and just have a look at the code that I've created so far, the structure of the code as well. I've done a little bit of restructuring since the last episode, so I want to talk about that and then talk about the basic outline of the new filled poly class, and talk just about that. And then after that, I want to come back and we're going to have a look at how we actually solve the problem of counting the number of edges of the polygon that we cross. Just before I jump to the computer, I just want to quickly say, as I always do, if you like this video, please remember to hit that like button. And if you haven't done so already, please remember to subscribe to my channel so you don't have to miss any future videos. Thank you very much. Anyway, right, let's go to the computer. Let's have a look at the code. Okay, so here we are at the computer, and as I've just been saying, one of the things that I've done since last week is that I've been working on a little bit on restructuring the code and everything that we've been developing. In particular, what I've done is taken more of the code out of the individual classes for the actual shapes and put it into the object class, into the base class. So what we're looking at here, this is object.h. And we can see what I've added here. I've added two new public functions to this, which avoid init texture for initialized texture. And I've added a function here to convert colors from a QBColor class into a uint32. Now, the reason I've done that is that it allows us to simplify the code quite considerably in terms of how we actually go about creating the texture. So this came about because I realized that actually the code to initialize the texture, if we just have a look at that code actually, let's go to object.cpp, and you can see here, this is the init texture code here, and from that you'll recognize this if you've watched the previous episode. This is all of the code really just creates the texture. So we define the red, green, blue and alpha masks, and then we check whether we're using big endian or not, byte ordering, set up our masks accordingly, and then we create our texture. We went over this in the previous episode, and so this really creates the mTexture member variable using SDL create texture from surface. And this is the thing, I realized that this code is never going to change. It's going to be the same for every class of shape that we're going to be using, and so there was every reason really just to take that code out of the individual class definitions and put it here into the base class so that we can simply inherit it. And note that it's not declared as virtual because we don't ever need to override it. It is just what it is. And same with convert color. So this is the definition here of the convert color function. Simply converts the color from a QB color class into a uint32. Again, we talked about this in the last episode. One thing to mention though, I did notice in the last episode I'd got the order of blue and red the wrong way round. So you'll notice now if we have big endian ordering, we have blue first, then green, then red, then alpha. And if we don't have big endian encoding, then we have alpha first, and then red, green, and blue. Okay, so that's pretty much everything I've done really in terms of the restructuring. And what I really want to talk about now is the new class that I've created. So I've created two new files. These are filledpoly.h and filledpoly.cpp. In fact, if we look in the terminal window first, so we can see these are all the files here, and then in the qblib2d folder, you can see I've created these two files here, filledpoly.cpp and filledpoly.h. And we're using a master header file called qblib2d, so we can just hash include qblib2d into our code, and that gives us access to everything that we need. And we can see if I go to that file here, I've modified that from last week. I've simply added hash include filledpoly.h here, so that will now bring everything in specifically for that. Anyway, let's have a look at filledpoly. .h. So this is the header file for the filledpoly class. It's very similar to the structure that we use for the, or virtually identical to be honest, to the structure we use for the circle class. So I don't need to say really too much about it. We just hash include everything that we need. We define this within the qblib2d namespace, just as we did with the circle class. And then we have our class filledpoly that inherits from the object base class. We define, of course, a constructor. So this is different to the constructor for the circle. Of course, it accepts as first input is a pointer to the renderer, and then we accept a std vector class object of type SDL point called vertex list, and we accept our color. So the point is the user can create an instance of this class, and they can pass to it an std vector class object containing a list of vertices out of which we're going to construct the polygon. As before, we have the destructor function, and we override the virtual function for get bounds as well to return the bounding box, and we have our render function. And I haven't yet defined any functions to return parameters. That's something to come back to later. With private functions, we have compute bounds and update. Those are exactly the same as we had for the circle class. So compute bound simply calculates the dimensions of the bounding box, and update is the function that actually performs the rendering, and it renders the shape into the texture. And we're going to have a look at that in a moment. And then a private variable, we simply create a variable mVertexList to store our list of vertices. That is, of course, in addition to the variables that we have defined from the base class. So this is back in object.h, and here we have our variables to store the color, the bounding box, a pointer to the renderer, and a pointer to our texture. Okay, so that's pretty much everything I wanted to say for filledpoly.h. And if we look over at filledpoly.cpp, this is really standard, just hash include filledpoly.h, of course, and then we simply define our constructor, which, as I've just said, accepts a pointer to the renderer, our vertex list, and our color, and it simply stores those. It doesn't do anything much with those, and then calls compute bounds to calculate the bounding box, and finally we'll call update that will cause it to render the two-dimensional shape into the texture, not onto the screen or into the window, but just into a texture. We have our destructor, we don't do anything with that, and then we have the getBounds function, simply returns mBounds. Compute bounds, this is a little bit different now. So to start with, we simply set some large numbers for these min x and min y. You know, if you think about it, what we're trying to do is simply calculating, you know, what are the minimum x and minimum y, and maximum x and maximum y values that would contain all of the vertices of the polygon that the user has specified. So we simply set these initially, min x and min y initially, to large positive numbers, max x and max y to large negative numbers. And then we simply loop through every point in the vertex list, and we extract the x and y values of that, and then we use this very standard way of doing things. If x is less than min x, then we set min x to x. If x is greater than max x, then we set max x, and so on. And you can follow that code through, and you can see that will just loop through every point, and at the end of that, min x and min y and max x and max y will contain the extents of the overall extents of the shape, which we can use to construct the bounding box. And we just need to make the bounding box very slightly larger than the shape, so we decrement min x and min y by 1, and we increment max x and max y by 1. it does occur to me that actually doing that is a bit risky. If we were right at the edge of the screen, that could potentially make min x and max y and min y negative, and those could go beyond. That is a good point. Something I will look at over the next week is to clamp those to the appropriate values, but we'll come back to that. I'm aware of the issue, I just haven't dealt with it yet. And then we simply update the bounding box. So the bounding box is an SDL rect structure, so we simply set x, y, and width w and height h accordingly. And then we have the update function. This actually does the rendering, so I'm going to come back and talk about that in a moment. And finally, at the end, we have the render function. This is exactly the same as the render function for the circle. Literally, it hasn't changed at all. All it does is create a SDL rect structure called source rectangle, configures that accordingly, and then uses SDL render copy to copy the texture from mtexture into mrenderer from the source rect and at the location specified by mbounds. So just if we look back at the update function, this is the critical function that really does all of the work, and this demonstrates the advantage of the new structure that I've used, whereas before I would have needed to have copy and pasted the code to initialize the texture basically from the circle class into the filled poly class. Because it's now contained within the base class, we can just call init texture here, and that initializes the mtexture member variable. And then all we need to do is set up our pixel buffer, which we do here. That's very straightforward. We use memset to set every entry of that, every byte in that to 0. And then we use the convert color function here to create our uint32 pixel color from our instance of the QB color class here. And we don't need to worry about this. Actually, I haven't used pixel color 2, but yeah. So this then is the main code that does the actual drawing of the polygon. And we've talked about that. What we do, I'm going to talk about this in more detail in just a moment, but what we do is basically here we loop over every pixel in the bounding box, and then for every pixel in the bounding box we then loop through every edge for the specified polygon. We extract x1, x2, y1, y2, x3, x, and so on, like so, and then we do the calculations to see if we have any intersections. I'm going to come back to that. So we talked about the basic algorithm. So I'm going to talk about the testing the intersection bits in a moment, but what we do is we simply count how many intersections that we have for every point, just as we talked about in the introduction there. And if that number is odd, which we test by simply using if count modulo 2, if that number is odd, then we set the pixel, because then we know that we must be inside our shape, so we set our pixel accordingly. If it's not odd, if it's an even number, we don't do anything. And that creates the texture in the pixel buffer, and then all we do is use the SDL update texture method to copy basically from temp pixels into mtexture. And that's it, and then delete the pixel buffer because we have finished. Okay, that is the basic structure, but what I really want to talk about is how does this work? How does this actual algorithm work to test the intersections? And I want to go over the maths about that a little bit. So let's just go and have a look at that now. Okay, so we've seen there the basic structure of the code that I've gone for and how I've decided to set this code out. What I want to talk about now is how we actually go about testing for intersections between the search line, that's the line that we cast out from the particular point that we're considering to the edge of the bounding box, and an edge of the polygon. How do we actually go about doing that? Well, it turns out really the simplest way that I found to do that is to simply solve the equations for the two lines. Okay, so as you can see here, we can represent our search line in vector notation as follows, and then we can also represent the edge, each edge of the polygon. So let's just consider just one edge of the polygon just to start with, okay? And we can do this then in turn for each of the edges. So we can represent both of those lines using vector notation, as you see here. Now, in order to find where these lines intersect, or indeed whether they do intersect, all that we need to do is to make the equation for one line equal to the equation for another line. And if we do that and separate it into the separate equations for x and for y, then we get the equations that you can see here. Now, in all of these equations, u and v are simply real scalar quantities that simply represent the relative position along the line. So x1 and y1, x2 and y2 represent the start and end points of our search line, and x3 and y3 and x4 and y4 represent the start and end points of the edge of the polygon that we're considering, respectively. Okay, so with a little bit of rearranging, we can make those equations look like this, and we can see quite clearly that this is a system of equations, two equations with two unknowns, and we can simply solve that the way we could go about solving any system of linear equations. And a nice way to do that is to represent it in matrix notation. So if we do that, if we take these equations and we write them out in matrix form, we get something like this. Now the challenge here is that we need to calculate u and v. Now to do that, we need to be able to take the inverse of the matrix that is shown here to the left of u and v on the right-hand side of the equation. Then we can move that across to the left-hand side of the equation and multiply that by x1 minus x3, y1 minus y3, and that will then give us the values of u and v, indeed, which will then, we can plug those values back into the equations and we can determine exactly where our point of intersection was. So the challenge then is, how do we actually go about inverting that matrix? Now if we just call that matrix A for the moment, then that's quite easy. So we know that we have x1 minus x3, y1 minus y3 multiplied by the inverse of A. Now, in order to calculate the inverse of the matrix, we're going to do it algebraically, and we're going to just use the determinant method. So the first thing we need to compute is the determinant of A, and we can do that as follows. I will leave you, if you wish, to work through the maths of this yourself, the algebra. It's not particularly difficult, so I don't really plan to go into it too much, but the equation for the determinant of A is here. And once we've got the determinant, we can then calculate the inverse of A as simply being the 1 over the determinant of A multiplied by this particular result that you see here. And then once we've got that, we can then quite easily derive the equations for u and for v, as you can see here. Again, I'm not going to go over that in any great detail. I'll leave that as an exercise for you, the viewer, if you want to work through that and check that for yourself. There are plenty of good resources actually online that talk about this, on Wikipedia and a number of other websites that have quite a lot of information on doing this, but it's quite a basic thing. The intersection of two lines is quite a regular thing. So algorithmically, computing all of this is potentially quite expensive, and there are going to be occasions where the lines that we're interested in simply do not intersect, so where our search line and the particular edge of the polygon that we're considering simply don't intersect at all. And in those cases, it would be rather wasteful to go on to calculate u and v, and in fact, it turns out that in cases where the lines don't intersect, then the determinant of A is going to be equal to 0. So even if we tried to calculate u and v, it would fail because the determinant is 0, we're dividing by the determinant, so that would be a division by 0, which is of course an undefined quantity, so that wouldn't work. So the first thing that we need to do in our algorithm is to compute the determinant and check if the determinant is equal to 0. If it is, then we know there's no intersection, so we don't need to bother doing anything else with that edge. However, if the determinant is not 0, then we can go on to calculate the values of u and v, and all we need to test then is whether the values of u and v are both between 0 and 1. And if they are, that means that we are between the points x1, y1, x2, y2, and between the points x3, y3, and x4, y4. And that means that the intersection occurs within the lengths of our two line segments. And that means that is an edge then that we need to consider. It is genuinely a point, an edge that we have intersected with, and so it's one that we need to consider. So the basic process is one of simply looping through every pixel in our bounding box, and for every pixel in the bounding box we cast a line from that position out horizontally to the edge of the bounding box, and then we check that line for intersections with every edge of our polygon, and we count how many intersections there are. If that number of intersections is even, then we know that the point must be outside the polygon. If the number of intersections is odd, then we know that we must be inside the polygon, and then we render a point accordingly. Okay, so let's go back to the computer and let's have a look what that looks like in code. Right, okay, so we've seen how the maths is done, how we've derived the actual equations. Let's just have a look how we actually go about implementing that in code. The first thing that we do, and we're in the update method of the filled poly class, the update function, sorry, of the update function of the filled poly class. And the first thing that we do to actually implement the algorithm, of course, is we define our internal variables x1, y1, x2, y2, x3, y3, and x4, y4, exactly as we've just seen in the equations. We need a variable to store our determinant. We copy the size, mVertexList.size, into a variable called n, and we define two floats for u and v. These are the real scalar quantities that I just talked about from the equations that ultimately what we want to derive. Okay, we then loop through every pixel in our bounding box, and for every pixel in our bounding box we are going to count how many times we encounter an intersection. Okay, so we then loop through every edge, and it's interesting to note here, so we loop through I from 0 to I less than n, so we'll loop through every vertex actually in the specified polygon. And then here, where we extract x3, y3, and x4, y4, these are the start and end points of each edge. So the start point is going to be the x and y coordinates corresponding to I, and then the end point are going to be the x and y coordinates corresponding to I plus 1. But notice we do I plus 1 modulo n. Now the reason we do that is so that it will automatically wrap around to the first point. So when I plus 1 becomes equal to n, then it will simply loop back to give 0. So it means the last point in the vertex list will create an edge that is automatically connected back to the first point in the vertex list. Okay, x1, y1, x2, and y2, those are just pretty obvious. So x1 and y1 are simply the x and y values from our loops, but of course our loops start from 0, so we have to add an offset corresponding to the location of the bounding box, and we simply add mbounds.x and mbounds.y. Okay, and okay, yes, and we do that, and then we simply are constructing a horizontal line, so the new x position is simply going to be the maximum extent of the bounding box in the x-axis, and the y value, y2, is simply going to be equal to y1 because we're just doing a horizontal line, so that's quite easy. Okay, so then what we do is we calculate the determinant, and we've just seen the equations for doing that, so I don't need to talk about those again. We simply implement that equation just like that, and that gives us our determinant value. If the determinant is equal to 0, then we don't need to do anything because we know that we haven't got an edge, an intersection. There's definitely no intersection if the determinant is 0. So we test if det A is not equal to 0, and if it's not equal to 0, then we know we have to do stuff. So we then implement the equations to calculate u and v, and we're static casting everything to floats because u and v are floats, and these are going to be values between 0 and 1. We don't really need as much precision as a double, so we just go with floats, and then we simply implement the equation here as we just saw. That's the numerator divided by static cast the float of the determinant, and we do exactly the same for v, do exactly the same for v, and divide by the determinant again. So we only have to calculate the determinant once, and we use it twice. And then we simply test that if u and v are both between 0 and 1, then we know that we have a valid intersection. If one or the other of u and v is less than 0 or greater than 1, then although we detected an intersection, we know that it doesn't lie within the line segments defined by the actual x and y coordinates. If we've detected a valid intersection, then we simply increment our counter, and then we carry on. We loop through the rest of the edges, increment the counter every time we detect a valid intersection, and then we come back to here. If we detect that count isn't, once we get out of that loop, we drop out of that loop, and then if count contains an odd number, then we know we must be inside the shape, so we render a pixel. If it's an even number, we don't need to do anything at all. Okay, and that's it. It seems quite complicated. It isn't particularly, it's actually rather a nice algorithm, and I do believe it probably could be implemented in a more efficient way than this, which would be faster, and that is something that I'm going to maybe look at over the next week. But this is the most sort of basic way of implementing that I could think of, and I think it's rather nice. You know, the whole way of detecting whether you're inside the polygon by simply counting the number of intersections with the edges of the polygon and seeing if that's odd or even, I think is really just quite a nice way of doing it. Anyway, let's have a look at what it actually does in practice. So if we go back to our terminal window, so we set up the makefile in the first episode, and of course we set that up so that it would automatically detect new files, so we don't need to do anything with that. We can literally just run make, and that will go through and it will compile the files, and we'll see it'll go into the QBlib2D folder and it will automatically pick up filled poly. So there we go, that's our code. And right, okay, what I didn't do. Well, yes, all right, let's just run our code. And there we go. So we see that as it stands at the moment, that draws a yellow triangle, which is not very exciting in the top left corner of the screen, but we can see that is a filled polygon shape. So clearly everything is working. Now what I want to do, just have a look at capp.cpp. So this is the file that contains, this is the actual class for the application. We've talked about all of this before, I don't want to talk about it too much, but it does show how we set this up. So all we do is we create a std vector object of type SDL_point called test vertices, and then we initialize that with the vertices. These are the ones corresponding to the triangle that we just saw. And then we define an instance of the filled poly class called test poly. We pass to it a pointer to the renderer. We pass the std vector object we just created with the vertices, and we specify the color, which of course in this case is yellow. And we then, I put in some code here just to test that we correctly compute the bounding box, so that extracts the bounds and displays them. And then we call testpoly.render to actually render the shape onto the screen. So when we call the constructor here, this will create the texture. That will actually perform the task of rendering the shape into the texture. And then we call testpoly.render that will actually render it to the window. That's what we're doing. And we can prove that it works if we look at some different shapes. So that was a triangle. Let's look at a basic rectangle like that. If I go back to my terminal window, let's just run make again. See, the great advantage of doing make, it only compiles the file that has changed. Let's just run our code. And yes, now we see we have exactly as we expected a filled square. In fact, not really. It's a special case of a rectangle, a filled square. And I made one already, which is slightly more complicated. You can see there's a few more vertices defined. And if we have a look at that, let's just run make. Okay, and let's run our code, and there we go. So we can see we have successfully implemented an algorithm that draws filled polygons, including ones with quite slightly more complex shapes. This one is concave rather than simply being convex, which does demonstrate that the algorithm is working correctly. A reasonably important test to do. One final point just before I leave this for now. I am aware that the run times of this can be quite long. That took 19 milliseconds, really? Yeah, so that's quite slow. So we're looking, that was 11 milliseconds, and we run it again, 8 milliseconds. Okay, getting a bit faster. 6 milliseconds. It really seems to get faster every time. Look at that. 7 milliseconds. Okay, so I mean, we're talking. I think these really long values, this will depend a lot on my screen recording, of course, it is running now. That will make everything slower than it needs to be, but it is not that fast. I mean, for rendering a single polygon, it would be better if we could get that below 1 millisecond into, you know, hundreds of microseconds really would be the target. But as an algorithm, it really works. And the one point that I would make is, of course, because we're rendering it into a texture, actually rendering it onto the screen takes virtually no time at all, because we're just blitting that texture into the window. And over the next week, one thing that I want to do is to extend this code, probably actually in the object base class, because I think it will be something that will go into for every shape. I want to be able to move the shape around on the screen without having to adjust, without having to re-render the texture, if you see what I mean. It doesn't make sense. At the moment with this filled poly class, if we wanted to move the filled poly to somewhere else, we would have to modify these vertices, and we would then have to cause it to re-render the texture, which would be very slow, and is actually completely unnecessary. If we just wanted to move it around, we just need to plot the texture, to blit the texture into a different place. Anyway, that's all things that I'm probably going to look at over the next week, but we'll see. So there we go. Okay, so that's really everything I wanted to talk about today. We've covered the basic algorithm for rendering filled polygons that we're going to use for our 2D primitives library. And we've looked at really basically how that works, that we, for every point in our bounding box, we simply cast a ray out horizontally to the edge of the bounding box, count the number of intersections with the edges of the polygon. If that number is even, then we know we're outside the polygon. If it's odd, we know we're inside the polygon, and we render the pixel accordingly. And we've seen how that works, and we've seen a way of implementing it. Kind of thinking that the way I've gone about implementing this is actually a little bit on the slow side, and I think it might be possible, I'm not really sure, I think it might be possible to optimize this further, and that may well be something that I'm going to look at over the next week. I'm also keen to look at doing some different shapes and maybe some interesting things with the sign distance functions that I alluded to at the beginning of this episode. I'm not sure exactly yet. But the code that we've looked at today, the code I've created so far, this is the basic algorithm for rendering filled polygons. And one of the things that I would say on that score, because of the way that I'm doing this by rendering the two-dimensional shape into a texture and then simply basically blitting that texture into the window at the relevant position, we only actually need to create the two-dimensional shape once, unless the code requires some kind of dynamically varying vertices for our polygon or something. We're not needing to regenerate it every frame if we were using this for animation. So one thing that I want to do is to extend the code so that we can change the position of the polygon on the screen without having to redefine every vertex. And because we're rendering it into a texture, we should be able to do that very easily, simply by changing the position in the window into which we blit that texture. And that will be very, very fast. So in that instance, we only need to create the shape once. We only need to render the texture the one time when we create the instance of the class. And then there's no need to do anything with it again. So it should be perfectly fast. And on that basis, I'm thinking that for what I have in mind to do with this code, it doesn't matter so much if the implementation of the maths for calculating the intersections is perhaps not as optimum as it could be, simply because, you know, I'm unlikely to need to do that again after the polygon has been created. Anyway, like I said, that's really everything for today. I'm going to carry on working on this, and hopefully next week we'll have something more interesting to show you in terms of what we can do with our 2D library. But basically the basic functionality that I wanted to implement is more or less all there. Just some specific special case shapes that I wanted to consider. And I also, as I've said, I want to bring in better support, or indeed some support for doing animation. So hopefully in the next episode we'll be able to look at something like that. And, well, anyway, I really hope you've enjoyed this episode. It's been a great deal of fun making it, and I really hope you've got something useful out of it. If you've liked it, please remember to hit that like button, and if you haven't done so already, please remember to subscribe to my channel so you don't have to miss any future videos. I do try to make one every week. Don't always make it. Sometimes things get in the way, the day job and whatever, of course, but that is what I try to do. So if you subscribe, then you know for sure that you're not going to miss anything. Anyway, listen, it's been a pleasure. I really hope you've enjoyed it, and I really look forward to seeing you in the next video. Thank you very much for watching. Bye.